When it comes to computer graphics, vectors reign supreme. From game physics and player movement to lighting calculations, especially in older games like Quake, they are indispensable in modern gaming, as every frame on screen involves thousands of vector calculations. But the problem is that vector calculations are expensive. So instead of working with full-length vectors, we normalize them by scaling them down to a length of 1. And one key step to normalize vectors is by taking the inverse square root for computational efficiency. During the development of Quake 3 Arena, developers noticed that the standard square root and division functions were simply slow and expensive. In times where memory was precious, this was not a feasible solution, as performance meant better success. The developers at id Software, with the help of other pioneers in the industry, coded a function to approximate the inverse square root from scratch. And at that time, the result was a gaming revolution for graphics and performance. And the rest was history. We will iterate through the code line by line to approximate the inverse square root of 16, which is 0.25. The first 3 lines are variable declarations used in the end to refine the approximation. For example, if our solution is 0.23, these will improve the accuracy to 0.24. We then store our number 16 in the variable y, and its half in x2. Now, to avoid division, we must use integers, as they can be easily bit manipulated, unlike floating points. But the problem is that if we convert floating points to integers, the bits are completely different, hence giving us the wrong approximation. To get around it, the developers took the address of float number 16, cast it to an int address, then read the value at that address as if it is an integer and assign it to I. Now our float number 16 can be represented as an integer, which we can now manipulate, as they are of the same value but with a different interpretation. To confirm this, we will convert the integer I to binary, then convert the bits to IEEE floating point format, and we end up with 16 again. This means any change to the integer I will affect our floating point number 16 accordingly. That is why the comment states evil floating point bit level hacking. We manipulate our integer as if it is a floating point number. As we did not convert, we simply read the float's memory address as an integer address, and the dereferenced value will behave like one. And by the way, this line violates C's type safety rules, because it is reading memory as a different data type. But the compiler accepts it, but technically, it is an undefined behavior that works. This brings us to the next line. Right-shifting I by 1 means dividing it by 2. This is the bit manipulation that we mentioned, as it is way faster than the standard division. We then subtract it from the magic constant, and we end up with the integer solution. To check the approximation, we convert it to binary, then to the IEEE format, and we end up with 0.50075, which is very close to our goal. This works because if we log the IEEE float format, we see that the logarithm of our number equals the exponent plus the mantissa, meaning we can approximate the bit representation of that number by its own logarithm. Let's keep this in mind. We must remember that a square root is a number half-powered, and the inverse is the negative of that exponent, which is our goal. Using the previous logic, logging the inverse of the square root gives us log 2 of our number, meaning its bit approximation multiplied by minus half, which explains the addition of minus I right-shifted once. And that is why we avoid the division operation. This simply means if we can approximate the bit representation, we can apply the same logic of approximation on our function to get an accurate solution. Now you might be wondering, where does this hexadecimal constant come from? Through empirical findings, this constant is approximately 3 over 2 times 2 to the power 127 times 1 minus mu, where 2 to the power 127 relates to the IEEE 754 exponent bias 127, and 3 over 2 comes from the mathematical derivation of that format. And mu is a small adjustment factor chosen to minimize error across the range of all possible inputs. Now our approximation is an integer that needs to be reinterpreted as a float, which brings us to the next line. To get our solution, we must reinterpret the integer bits as float bits, just like the previous line, and we end up with the binary value of our solution. We convert it to decimal, and we get our first approximation. Close enough, but it needs refinement. The next step involves Newton's method to find a solution to a function. We take the guess from the magic constant solution, and we then see how far we are from the actual solution and adjust it accordingly. In our case, this is where we are, and this is what we need to aim for. We take the derivation, which is the tangent, and we get our new guess, which is very close to 0.25. Although Newton's method involves division, the code uses multiplication instead, and by plugging our declared variables to refine the result, in one iteration we get 0.4999, which is incredibly close to our goal of 0.25, proving that the code works without division and successfully approximates the inverse square root of 16. Modern code can run this logic even faster, but at that time it was legendary, especially considering the math and the minds behind it, as it showcases the beauty and art of programming before the age of Stack Overflow or AI, and what we take for granted when we play these legendary games. Thank you so much for watching. Until next time.